Hello, we learned a Carnot heat engine is a hypothetical engine in which all the processes are reversible. A Carnot engine works based on a Carnot cycle. Suppose if a Carnot engine is reversed, it works as a refrigerator and heat pump. What are they? We will discuss in this video. We will learn about refrigerator. Remember, refrigerator works on the principle of reversed Carnot cycle or a reversed Carnot engine. What is this refrigerator? It is a device which keeps a body at a temperature lower than that of its surroundings. A schematic of the refrigerator device is shown here, and there is an evaporator. Evaporator is the body whose temperature we aim to keep lower than that of the atmosphere. Atmosphere means the surroundings. So atmosphere is at a higher temperature. The evaporator is at a lower temperature. That means we aim to keep that at lower temperature. How is it possible? For that we need to take heat Q1 from the evaporator and reject it through a condenser to the atmosphere. Condenser is at a higher temperature T1 because it is at the atmosphere. Atmosphere is at higher temperature. This process is impossible because naturally heat flows from a body at higher temperature to a body at lower temperature. But here we aim to take heat from evaporator which is at lower temperature and reject that heat to condenser which is at a higher temperature T1. In order to make this possible, we need work input, and that work input is supplied through the compressor. Also, we need another device, expansion valve. So how this practical thermodynamic refrigeration cycle works will be covered later. Right now, we studied the principle of a reversed Carnot engine, which is nothing but a refrigerator. Simply put, a refrigerator has to take heat from a body at lower temperature and delivers it to a body at higher temperature. Schematically, it is shown here. So there is a body at temperature T2, there is a body at temperature T1. T1 is greater than T2, and this refrigerator has to take heat from the lower temperature body to and reject heat to a higher temperature body. Naturally, it is impossible. For that, we need to give work input, which is equal to Q1 minus Q2 for the refrigerator. To study how efficient the device refrigerator is, we define a term called coefficient of performance, abbreviated as COP. COP is defined as desired effect divided by the work input. What is this desired effect? We need to maintain a body at a lower temperature T2. How is this possible? This is possible by removing heat Q2. If you are able to remove Q2 from the source, then it will be maintained at a temperature T2. Therefore, our aim is to remove Q2, and hence the desired effect is Q2. Heat transfer from a cooler body to a hotter body is not natural. Therefore, we need to supply work input. That work input is equal to Q1 minus Q2. So that is a work input. COP of a refrigerator is equal to Q2 divided by Q1 minus Q2. Now we will learn about a heat pump. It's a device that keeps a body at a temperature higher than that of its surroundings. Like refrigerator, here we define coefficient of performance as desired effect divided by the work input. But the desired effect here is Q1. And what is this Q1? The schematic of the heat pump is shown here. The aim is to keep this reservoir at temperature T1, and T1 is greater than T2. T2 is the surrounding. In order to keep a space at a temperature higher than that of its surroundings, we need work input, and that work input is given to the device called heat pump. In order to maintain this temperature T1, which is greater than the surrounding temperature T2, we need to add heat. We need to add heat to this reservoir. For that, this heat pump takes heat from the surroundings and delivers the heat to the space whose temperature is to be greater than the surrounding. That's shown here. So Q2 is taken from the surrounding, Q1 is delivered to the sink. So what is the desired effect? The desired effect is Q1. That means in order to maintain the temperature T1, we need to supply Q1 heat constantly to the space. Therefore, the desired effect is Q1. And what is the work input? Work input is the difference between these two heat transfer quantities, that is from first law of thermodynamics. And of course, this is the net work input, Q1 minus Q2, shown here. And if you compare the coefficient of performance of a refrigerator and a heat pump, we will easily deduce coefficient of performance of a heat pump is equal to COP of a refrigerator plus 1. We learned a refrigerator and a heat pump, both working on the principle of reversed Carnot cycle. It's time to define Clausius statement of second law of thermodynamics. What it says, it is impossible for a device which operates in a cycle will produce no effect other than transfer of heat from a cooler body to the hotter body. Naturally, heat flows from a body at higher temperature to a body at lower temperature. The reverse is possible only through some work input. Those devices which performs heat transfer from a cooler body to a hotter body by taking work input are termed as refrigerator and heat. We defined so far two statements for second law of thermodynamics. One is Kelvin-Planck statement, the other is Clausius statement. What is Kelvin-Planck statement? For an engine to work, there must be heat rejection. What is Clausius statement? For transferring heat from a cooler body to a hotter body, we need work input. Are they two different statements? No, they are equivalent. How? We will prove. For that, consider two reservoirs. One is at T1, the other one is at T2. T1 is greater than T2. And assume there is a heat engine, HE, which takes heat from the reservoir at T1 and delivers some work, W net, which is equal to Q1. Obviously, this violates Kelvin-Planck statement. Therefore, it is impossible. So this engine is impossible, but assume it is working. Also assume there is a heat pump which works between the reservoirs at T1 and T2. Remember, a heat pump is a reversed Carnot heat engine. Therefore, it takes heat Q2 from the reservoir at T2 and rejects heat Q1 to the reservoir at temperature T1. Naturally, this is impossible because T1 is greater than T1. But it is made possible by supplying work input through the heat pump. What can we do now is supply the net work delivered by the hypothetical heat engine HE. Therefore, this heat engine and heat pump together constitute a device which maintains the reservoir at a temperature T1 greater than that of its surroundings at T2 by taking no work input. So there is no external work input. The work input is given by this hypothetical engine itself. So these two devices enclosed within a space, that means a control volume or a system, there is no external work input. The work input required by the heat pump is supplied by the hypothetical engine. So this engine is working violating Kelvin-Planck statement, hence it is impossible. When you combine these two devices, the heat pump is impossible. Therefore, violation of Kelvin-Planck statement violates Clausius statement also. So violation of Kelvin-Planck statement by the heat engine violates Clausius statement also. That means the heat pump violates now because it takes no work input from outside. And hence, Kelvin-Planck statement and Clausius statements are equal. We can prove this We can prove the equivalence of Kelvin-Planck and Clausius statement in other way also. Consider a heat pump and a heat engine operates between the reservoirs at T1 and T2. The temperature of reservoir at T1 or T1 is greater than T2. Assume this heat pump operates without taking any work input. So without taking any work input, it takes heat from a cooler body and delivers it to a hotter body. Definitely, this violates Clausius statement. But assume it is working. Look at here, this heat engine is taking heat Q1 from the reservoir at T1 and rejects Q2 to the reservoir at T2, delivering a net work output, which is equal to Q1 minus Q2. Compare the quantities of heat rejected into reservoir T1 and the heat taken from the reservoir at T1. They are Q1, both equal. Therefore, what can we do is we can remove the reservoir at T1 and connect the heat pump directly to the heat engine. Now, this heat pump and heat engine together constitute a device which operates in a cycle, producing net work output by exchanging heat with only one reservoir. This violates Kelvin-Planck statement. Therefore, violation of Clausius statement by this heat pump leads to the violation of Kelvin-Planck statement also. Hence, Kelvin-Planck statement and Clausius statement are equivalent. Thank you.